Hi, good morning, everyone. So we'll wait a minute or two for everyone to join us. I think some of you were confused by the change in the time zones and the moving back to standard time. So we sent a Piazza message. Hopefully everyone got it and they know. Good time to ask a question if anyone has a question before we begin. No questions. Okay, so this is just a reminder to you that election day is tomorrow. Hopefully all of you have already voted, those that can vote. If not, please vote tomorrow. And if you don't vote, because you cannot vote in the US, you can still understand the system a little bit better. So you can help change it once you can vote. This documentary is a good one. There are many others that are good. And we can move on to the class. So I'm hoping everyone recovered from the midterm and ready for the next part of the semester. So just a few reminders. This is the key one. Please follow the lectures follow the website in general, and look at the lecture notes even before the class, so you'll be ready. Homework 3 is going to be out today. The year is missing there, but it's due 2 weeks. I don't know what happened there. 2 weeks from today. You cannot solve all the problems yet, but hopefully within the next week, you'll be able to solve all of them. And also notice that it's less time consuming than the previous two. So there's no programming in this one. So I think it's a bit easier. So on average, the time you spend on homework is going to go down. This will allow you to spend more time reading the lectures and thinking about it. Midterms, I'm sure many of you have questions still. So these are the numbers that you've seen for the midterms. The numbers are relatively low, a little bit lower than I was hoping for, but the spread is actually good. And then the absolute numbers make no difference at all. So here's the distribution. And really what you care about is where you are relative to the class, because as I said at the beginning of the semester, and again on a Piazza message last week, this is basically the expectation for the class. About 35–40% of the students will get some kind of an A. The next 40% will get some kind of a B. The next 20%, the lowest 20%, will get some kind of a C. Hopefully, no one will go below that. Typically, people that stop doing the work at some point will get below that. So if you continue working on the class, do the homework, do the exams, quizzes, and so on, and attend, you'll do well. So basically, that's kind of where the line is. Above this line, you're going to get an A, pretty much. Below this line, you can still, of course, move above this line. We have more than half the work still ahead of us. Questions on this?
I just have a question on the project.
I'm getting to the project. Just a
sure,
second.
Okay,
So
right.
ask it after the next slide. Any question before the project on homework, midterm, anything else? Okay, recording. Yes, we are recording. And projects. Okay, so as you all know, CIS 519 need to do a team project. This year, most of you are in 519, which was a surprise to me, but that means that we have to do a little bit more work on it because it's not scalable. And therefore, what we decided is that, one, teams are going to be size of 2 to 4, no individuals. And we're going to help you grouping. I know that in the situation we are in now, it's a little bit harder to form teams. There will be 3 projects, and you will choose one of them. There's going to be one project in NLP, or basically text, one on vision, basically you'll process images, and the third on speech, you'll process audio files. In all cases, we're going to give you data sets and initial ideas. In all cases, the problem will be multi-class classification. And you'll get annotated data. And the key part of the project that we want to pursue is you're going to get annotated data only for some of the labels, but you'll have to classify also for other labels that you haven't seen annotated data for. So ideas like zero-shot learning, few-shot learning, transfer learning, all these are going to be things that you will play with. So you will choose the domain, which of the projects you want to work on, and you will choose specific things that you want to explore, of course. But beyond that, we will only have kind of 3 types of projects to review. Later today, we're going to send out a detailed note with details on the data sets and some initial ideas. And here's the timeline. So within a week, I'm hoping that all of you will choose a project and team up. There will be some suggestions for how to do this on Piazza. Within 2 weeks after that, we want to have from you a written 1 page. We're going to talk about it on the Piazza note proposal describing what your team is going to do. We're going to also have a progress report 2 weeks later, the first couple of days in December. And the final project is going to be due between the 15th and 20th of December. We don't know exactly when is our final exam, and we're going to schedule it relative to the final exam. The goal is going to be to write a short paper. It's supposed to look like a paper, and a short video. We're going to give instructions for that will basically describe what you've done and describe the key results. So even though we are choosing 3 areas, I think there's going to be a lot of flexibility still, and you can still make it very, very interesting. Questions?
So is this only for 519 students? So if you're in 419, this doesn't apply?
Doesn't apply. You can still do it, but doesn't apply. It's not part of your grade.
So just to confirm, the team of 2 is fine, although according to the project page, it should be 3 or 4 people.
Yeah, so we will accept also teams of 2. I would prefer teams of 3 or 4. We will not accept teams that are larger than 4.
Got it. Thank you.
So if we do need help getting into a group, should we reach out or?
So we're gonna announce it on Piazza later today. There's gonna be some. We're gonna use Piazza mechanism for doing it. But if you still need more help, please reach out to the TAs. Any other question? Okay, good. So of course, there's still going to be an opportunity to ask questions about it once we make more information available. So let's see, where are we? So this is where we ended up just before the midterm. We are looking for a theory that allow us to understand what the observed performance, the performance on the training data, says about future performance, and how can we understand this gap between what we see in training and what we're going to see or hope to see in tests, and how can we control it? So the picture you want to have in mind is this picture here on the right, where I have a function f, which is my target function. Everything inside this ellipse is positive example, everything outside it is negative examples. And what we learn actually is this H. So there are areas, these moons on the sides here, that where H disagrees with F, and we want to minimize this. So what we played a little bit with these ideas, and we said that we cannot expect a learner to learn a concept exactly. And we cannot always expect that it will even learn a close approximation to the target concept. Just because the distribution that we've seen in the training data with some probability will not be a typical distribution. Maybe the data set will be too small also. So with these two bullets, the only realistic expectation of a good learner is that with high probability, it will learn a close approximation to the target concept. And that leads to the definition of probably approximately correct learning, which is the key definition of learnability, where we require that given small parameters, epsilon and delta, small positive parameters, with probability at least 1 minus delta, that is with high confidence, a learner produces a hypothesis that has small error, at most epsilon. And that's basically the key definition. So this is a definition that I'm going to read out in more details now. This was a definition that was given by Les Valiant in '84 in a paper that is called The Theory of the Learnable. Still very good read for people that are interested in the foundations of learning. And in fact, there are still issues explored in that paper that the community hasn't dealt with completely. But here's the definition. We consider a concept class C, which is the set of potential hidden functions defined over an instance space X, containing instances of length n. We have a learner, L, that makes use of the hypothesis space H. That is, the learner learns functions that are in H. And we say that C is PAC learnable by L using H if, for all the functions in C, for all distributions over the instance space and some fixed small epsilon delta, the algorithm L, given a collection of M examples that are sampled independently according to D, produces with high probability, at least 1 minus delta, a hypothesis H that has error less than epsilon. And we require that M, the number of samples, is polynomial in the relevant complexity parameter, which is 1 over epsilon, 1 over delta, n, and the size of H. That's PAC learnability. In addition, we can require that it's efficiently PAC learnable. And this is an additional condition that says that L itself, the algorithm, is going to be efficient. So basically, we have two conditions. One we call sample complexity. How many examples do we need to see? And the second is time complexity. How efficient will the algorithm, should the algorithm be? And in all cases, computer science is all about polynomial complexity. And most of you should know this already. We require that the sample complexity is polynomial in the complexity parameter, and the efficiency, time efficiency, is polynomial in the relevant complexity parameters. So to be PAC learnable, there must be some hypothesis that has arbitrary small error for every function, every hidden function. But we already know that this will depend, this arbitrary small error will depend on some complexity parameter. For example, it will depend on the number of examples we're going to see and the size of the hypothesis. Okay, so notice that this definition is a worst case definition, right? So we say for every distribution, and we say for every hidden function. And of course, you can relax this requirement somewhat. It's not going to change a lot. And there's a lot of literature on various relaxations of this that we will not attend to in this class. For us, the important thing is that we kind of get the general gist of the theory, a theory that connects the observed performance with future performance. That's what we really care about. Questions so far? No questions. Excellent. Okay, so the key theorem that we have is what I call here the Occam's razor theorem, and you'll see in a second why. Really, it's the simplest, most possible way to phrase this theorem, but you will see that this is exactly the same theorem, or a generalization, simple generalization of the theorem that we proved for conjunctions. We took last time we took the very basic case of learning conjunctions. In fact, we did it for monotone conjunctions. We gave an algorithm, and we quantified how well will the algorithm do in the future. Now we can generalize this, and the claim that we're going to prove is the following. We're going to say that the probability that there is a hypothesis that, on one hand, it's consistent with M examples. That is, on the M examples we've seen, we made no errors, right? So our training was very successful. Nevertheless, its error is greater than epsilon in the future, right? The true error. So the probability that these two things are going to happen together is less than the size of H times 1 minus epsilon to the M. So how do you understand this? Basically, the key thing here is that you look at this term here and you say, okay, so the probability that after observing M examples, I still have a hypothesis that I'm not so happy with, right? Its error is greater than epsilon. This probability goes down exponentially fast in M, right? So if epsilon is 0.1, 10%, so what you have here is 0.9 to the M, and this goes exponentially fast down as M grows, which is a good thing, right? So as you see more examples, you shrink the gap between what you see on the training data, which in this case is 0 because it's consistent. There's no error on the training, and the true error that you will see. And of course, everything here is multiplied by the size of the hypothesis space, which is an important thing to know. So the more expressive the hypothesis space your learning algorithm can choose from, the larger the error you're going to make. Right? So we know that the variance, if you want, grows. So two comments here. One is this notion of consistency, right? So this is really the ideal situation. The learner is perfect on the training data. We call this the consistent learner scheme. And you'll see in a second why, because basically it gives me kind of a way to learn, a way to PAC learn hypothesis. But basically what we are asking here, how good are we going to be in the future if we are perfect in training? Of course, we want to generalize it later to the more realistic scenario where we are not going to be perfect in training. But this is the key theorem, and I'm not going to go into the details of how to prove it because you've already seen the proof. It's exactly the same proof that we've seen for conjunction, so just read it and convince yourself. Two comments. One is this notion of f, the hidden function, is really something imaginary. We don't really need to assume that there is a true f. There is something that labels the data. You can just think about it as a distribution over x cross y. The same argument goes here if you don't have an f or you don't know what f is, there is just a distribution that labels your data. So that's one. The more important question here is, so what is m, right? So that's really what you want. So I gave you this claim here. But really what you want to know is, okay, I give you epsilon. I want 5% error, no more than that in the future. How large should m be? So what we want to do is we want to take this expression here and isolate m from it. And again, we did this for conjunction. I'm giving here a little bit more details of how to take this expression, size of h times 1 minus epsilon to the m, which I want to be bounded. I want it to be less than delta, which is my confidence parameter, or 1 minus my confidence parameter. And I want to know, how do I isolate m from here? So again, same way I did it before. You take the log, you use some inequality that comes from Taylor expansion of e to the minus x, and that gives me m. So again, this is a little bit of algebra that I can count on you to do. But let's look at the expression that we get. If I want epsilon error or less than epsilon error with confidence at least 1 minus delta, I need to take these many examples. And you expect, so how do we understand this term? It makes sense, hopefully, that m goes up as epsilon goes down, right? If you want small error, you're going to pay by looking at more examples. If you want more confidence, that is smaller delta, you're going to pay for it by looking at more examples. And it also goes up with the size of h. The more functions the learner considers, the more examples you have to see. And this is really why we call this the Occam's razor theorem, because it for the first time, we see a quantitative way to think about simpler is better, right? Simple functions, less hypothesis is better because you need to see less examples for a given epsilon. Questions? No one is active on chat, at least. Oh, okay, here is one. Okay, excellent question. How can we determine the size of h in the general case? So we're going to get to it today. In fact, this is most of what I'm going to talk about today. How do we know what is the size of h? And really, there are two ways to think about it. So first of all, before I get to the size of h, I want to which will come in 2 slides, I want to kind of focus on this consistent learner scheme that basically this Occam's razor theorem came for it, right? It's assuming that in training I'm consistent. So essentially what we showed is that if I have an M consistent hypothesis, that is, I have a consistent hypothesis that I used M examples on, so it was consistent for my M examples, it generalizes well as a function of H. So why should we care about this? This is a repeat of what I said at the beginning, but it's really important for us to digest this. We care about it because now we have a theory of generalization. We know what are the important complexity parameters, and we understand the dependence between the number of examples and the size of the hypothesis class. And through this, we also understand the dependence between performance we're going to see on training and performance we're going to see in the future. And we also have a generic procedure for learning. A generic procedure that is guaranteed to generalize well. Draw a sample of size M, develop an algorithm that is consistent with it, 0 error on the training, and that will be good. If, of course, M is large enough as a function of the size of H. So, so basically we have this procedure. The procedure is take a set of M examples, find some H in H that is consistent with all these M examples, check that M is not too large, right? We want it to be polynomial in the relevant parameters. And we show that this is the expression. And basically showing that M is not large enough amounts to showing that M scales well with the log of size of H. And now we are getting, and let me just summarize this. In the case of conjunction, we show this, right? So we use the elimination algorithm to find a consistent H. Remember that we had a function that was consistent with all of the training data. We already knew that it's not the right function because I told you ahead of time what's the right function, but we don't care. We just know that it was consistent with our training data. And we directly showed that if we take enough examples, H is going to do well in the future. It's going to make small error in the future. Now we can do this in a more general way, and I'm going to go back to conjunction. So we didn't really have to show this directly because we can take our Occam's razor theorem that we just showed and instantiate it for conjunction. So, and this goes back to the definition, to the question that you asked, how do we know what the size of H is? So in some cases, we can just count. In some cases, we'll have to resort to a more complex notion that we'll get to a little bit later today of size. But let's take conjunctions. In conjunctions, we know that the hypothesis space has size 3 to the n. You all know this. And the proof is here if you forgot. So I can instantiate my Occam's razor results where ln of 3 to the n is here. Ln of 3 to the n is really n times a constant. And I know now that m is polynomial in the complexity parameters. I can plug in some numbers if you'd like, and you can see the numbers here. But the important thing is that because we already have an algorithm for learning conjunctions, and in fact, I don't care which algorithm we use here, because as long as you give me an algorithm that produces a consistent hypothesis, everything that is on this slide holds, because I showed you that you can supply to this algorithm these M examples, and you prove that it's PAC learnable. Now, of course, we can take other hypothesis spaces and argue that for them. And in the slides, I'm going to show a few more examples, but I will not go over them in details. You will just play with it at home when you read the slides. And basically, these are tools that will allow us to prove that things are PAC learnable. So one example that I show here is of KCNF. KCNF is a more expressive class of functions. It looks like this. KCNF is a conjunction of disjunctions. And the K here stands for the size of each one of the disjunctions. Right? So let's think about it as the function that says this or this or this or this, and this or this or this or this or this, and this or this, and so on. So it's a conjunction of disjunction. It's a very expressive class of function. And you can show that this is learnable. And basically, there are two steps. The key step is counting. And I'm doing it here. You will have to think a little bit about it. This shows that the log size of h is polynomial in n. So sample complexity-wise, you're okay as long as you have an algorithm. You need still to show me that you have an algorithm that can take examples consistent with these kind of functions and learn it. And the next slide is about an algorithm. Again, I'm not going to give the details. You'll read the slide and think about it. The key trick about this algorithm is that it requires blowing up the feature space. And I'm explaining here how to blow up the feature space, and you'll have to read it and understand. Okay. So there are many results for learnability, huge amount of literature, both for positive results to show that a class of functions is learnable, and to show that a class of function is not learnable. And there are two types of results for non-learnability, which is perhaps the more interesting one. There are complexity theoretic ones that talk about efficiency. You cannot learn this class of function efficiently because there is no algorithm that will minimize the error and is efficient in the complexity parameters. And there is information theoretic non-learnability results that say that there's no way you can learn function in this class with small enough examples. You need exponentially many examples. So just to, without details, just to give you some ideas, neural networks would be the most interesting example from your perspective. It's not learnable efficiently. And this is true even for neural networks with very simple architectures. Read one's Boolean formulas, for those of you that understand Boolean formulas or understand Bayesian networks, which we're going to get to at the end of the semester, read one's Boolean formulas are some kind of, can also express graphical models like Bayes nets, and they are not learnable. But even from information theoretic perspective, if you think about the class of all DNF formulas or all CNF formulas, or equivalently, all Boolean functions, this is not learnable. The class is just too large, and there is no way that you can learn it with a polynomial number of examples. Interesting classes like deterministic finite automata or context-free grammars are not learnable. There's no way that you can use a polynomial number of examples in the relevant complexity parameter and learn these from examples. By the way, this is a very interesting class of functions of, let's say, context-free grammars, where you cannot learn it from examples. But if you go back to a few weeks ago when we talked about active learning or learning by asking a teacher, it's possible to show that while finite automata cannot be learned from random examples, they can be learned by posing questions to a learner. So there is some interesting gap between these different learning protocols. Again, we're not going to get into it. If people are interested, I'm happy to give you pointers. From our perspective is we wanted to give a theory for learnability. And we have some notion of learnability that you can that you understand now, but it still has two holes, this theory. One hole is I only talked about, I gave this Occam's razor theorem for a hypotheses that are completely consistent with the training data. And that's too unrealistic, right? Because in real life, you will try to learn a good hypothesis on the training data, but it will not have zero error. It will have some non-zero errors. And the second non-realistic component is that I do everything in terms of the size, the number of hypotheses in the hypothesis space, but what if the hypothesis space is infinite? So we have to deal with this case too. So let's deal with the first one first. So, and the first one is called agnostic learning. So now we are assuming that we try to learn a function using hypothesis in H, but F itself is not in H, which means there's no chance that I will be able to get zero error, right? Because the function I'm trying to learn is very expressive, more expressive than the function my learner is using. So in this case, our goal should not be to get a consistent learner, but rather a learner with small training error. This is my training error. So what I want now is to guarantee that a hypothesis with small training error will also generalize well, will also have good performance on unseen examples. This is the true error, right? So error on the distribution, D, as opposed to error on the training data, on the M examples. And what I want is this generalization bound, which basically you can view as a bound on how much the true error on D, deviates from the observed error on training. And this is what we can show for this more general case. For any distribution D, distribution that generates training and test instances, right? Remember that the key assumption here is that there is one distribution that governs the generation of training and test instances. If that's not true, there's nothing we can say really, or very little we can say. But under this assumption that I have this distribution that generates training and test instances, with high confidence, that is with probability at least 1 minus delta over the choice of the training set of examples. For all hypotheses in H, we can show that the true error on D, is bounded by the training error plus some complexity parameter. And really, that's the most important theorem or type of theorem that you have for learning theory. I mean, there are of course a lot of variations of this, but this is the key thing, right? So, and in fact, in some sense, we've kind of seen that before, because if you go back to the online lecture, we've seen an expression with that form already. What is this form? This form is, oh, something is moved here. Let me just move this so you can see what I want to show. Okay. So the first term here is the error on the training data. And the second term, this complexity term here, is the generalization term. And again, the important thing is that you can expect already. It's a function of M, right? So the gap between the training error and the true error is going to go down as M goes up. And it's a function of the size of H, right? So if you have a lot of H's, this gap is going to go up. And of course, it's a function of the confidence, right? If you want more confidence, which means you want delta to be small, this gap is going to go up. So that's the key theorem. In the next slide, I'm kind of giving you an idea of how why this theorem makes sense. I'm not going to get into it now. I'm just going to show it here for people that are interested. The way you can think about it, okay, it's this slide, is kind of like tossing a coin, right? So if you toss a coin and you observe, you toss it 100 times and you observe that 43 times you get tail. What is the true probability of the coin? It's not 0.43, but you can say something about the gap between the observed error, the observed number of tails and heads, 43% tail, and the true probability of the coin. And of course, you can imagine that this gap between the number of tails that you get and the true probability of tail goes down, and in fact goes down exponentially fast with the number of coin tosses that you're making. If you'll toss 10, you cannot really count on the observed count, but if you toss 1,000, it's going to get there pretty quickly. And this is exactly the math that guides what we are doing here. You can think about you running your hypothesis M times on the observed examples, and you count how many errors you're making. This is the observed number of tails in the coin tosses. And you want to limit as a function of this, what is really the true error that this hypothesis can make. So this is something that is called hefting bounds. We're not going to get into it unless you really care about it. Okay, so now M. I showed you this theorem, but I want to isolate M again. And with the same algebra that we've done before, I can isolate M. And again, I'm gonna read out loud this theorem. So what do we have? We have a learner that is now agnostic. We don't know whether the hidden function is even expressible using our functions in H, but we don't care. What we want our learner to do now is to return a hypothesis with the smallest training error possible over the M observed examples. And for this H, we can guarantee that with high probability, at least 1 minus delta, its training error is going to be less than epsilon away from the true error if we take these many examples. And these many examples is, of course, something that goes up with epsilon. You want small error, you'll have to pay with more examples. Is going to go up with the confidence delta. You want to have high confidence, you're going to take more examples. And it goes up with the size of H. So basically, the bottom line of what we've shown so far is that learnability really depends on the log of the size of the hypothesis space. Questions so far? No questions. Okay, So now that we said, okay, so learnability depends on the size of the hypothesis space. We gave one example of a concrete hypothesis space that you can count. And there was one example that I left for you to think about. But still, what is this size of H? I mean, most interesting hypothesis spaces that we're going to deal with are not finite. So what do we do then when we cannot say size of H? Here is a simple example of that. Let's assume that I want to learn rectangles in the real plane, right? So you can think about X to be, height and Y to be weight. And you want to know the concept of, an NBA player. They have to be between some height and some other height, and between some weight and some other weight. So I'm going to see examples, positive example, negative examples, and so on. Some other example, and so on. And I can ask you, can you learn this rectangle? Can you give me an algorithm, let's say, that when given positive and negative examples, and it comes from a rectangle in the plane, will return a rectangle? Any suggestions? Think a little bit about it. What would be an algorithm that takes examples like this in the plane, and the hypothesis space is the space of all axis parallel rectangles in the plane? What would be your learning algorithm, or in fact, what will be your hypothesis that you will return as a function of these examples? Can you imagine? You can unmute and make a suggestion. Max xy, min xy. Okay, let's interpret this. It's true, but some details are missing. But let's start with this. So basically, the suggestion is, I assume, you want to look, say, only on the positive examples, forget negative examples, and take over the x-axis the max x of positive examples, and take the max and take the mean x over positive examples. So this gives you two numbers. In this case, it's this number, the mean x and the max x, and do the same for y. Then takes the mean y of positive example and the max y of positive example. Disregard negative. And now you have an algorithm and you have a hypothesis. And this hypothesis is consistent with all my examples, right? Everyone agrees that that's a good algorithm. So what was missing from the comment in the chat, that we're doing this only over positive examples? Okay, so yes, you can learn, but what's going to be the performance in the future? Can we quantify the performance of this algorithm in the future? Is it going to be good? And the answer is, we don't have a theory for this, because the number of rectangles in the plane is infinite. We cannot tell you how many are there. So we need to extend our theory to deal with hypothesis spaces that are infinite. For example, we want to deal with rectangles in the plane. We want to deal with linear separators. That is the output of perceptron on SGD and so on. How do we deal with it? So what we want is a theory that allows us to deal with infinite hypothesis spaces. So what I'm going to outline in the next 20 minutes or so is really a beautiful theory that allows us to extend from finite hypothesis spaces to infinite hypothesis spaces, and it allows us to quantify learnability in the general case. So now you can say all these hypothesis spaces, rectangles, polygons, linear functions, linear threshold units, and so on, these are all infinite. But intuitively, there are infinite spaces of different sizes. For example, if you think about rectangles versus 70 sides convex polygons versus all convex polygons, the larger class here is this one. Or you can think about linear threshold functions, just linear separator that SGD learns, versus conjunctions of linear threshold. So you have several linear threshold units, and you learn this and that and that, or this and that and not that. Again, the conjunction is going to be more expressive. So how do we express the fact that this is more expressive? And the notion that we're going to use in order to measure the expressiveness of infinite hypothesis space is this is a notion that is called the Vapnik-Chervonenkis dimensions, VC dimensions for sure. This is the last time I said Chervonenkis. And we're going to see that this is analogous to the size of H. And all the bounds, all the Occam's razors that we showed before, we can take size of H, replaces with VC dimension of H, change maybe a little bit the constants, and we have a bound for the sample complexity. Or if you want, a generalization bound that quantifies how the real performance in the future is going to depend on the performance that we see on the training data. Okay, so the key notion that we're going to use here is that of shattering. So you see here a number of examples, I think 14 examples here. Now these 14 examples can be labeled in many, many different ways, right? Let's assume it's two labels, positive and negative. You can label it in many different ways. And the question is, given that I have these examples and there are many functions that live on this set of examples, some of them just label this example positive and the rest negative. Some of them label these two as positive and the rest negative, and so on. We're going to show that the expressivity of the functions can be measured by how many of the configurations of this set of examples, how many of the label configurations can be expressed by a set of functions. So let's start with a simple case where we have just two examples. Two examples. How many ways can I label two examples? I can label it this way. The one at the top is positive, and the one at the bottom is negative. And I can separate this, I can express this function with a linear function here. The green line separates positive on top, negative below. The other way around could be that I have positive at the bottom and negative at the top. Also a linear function is going to do it. So linear functions are expressive enough to shatter 2 points. That is, to express all possibilities of labeling 2 points. In fact, there are 4 options to label 2 points. It could be one positive, one negative, as I show here. It could be the other one negative and the other one positive, but it could also be 2 positives and 2 negatives, which I don't show here. But in all cases, I can express all these functions, all these possibilities with a linear function. Everyone agrees, I hope. Let's go back to my 14 points. So here is one way to label my 14 points. Right, so I have blue and yellow points, red and yellow points. And I can separate it with a linear function too. But if I label it this way, linear functions are not going to do, right? So no linear function that you try is going to do it. In order to shatter this set of, I don't know, maybe 13 points, linear functions are not expressive enough. There's no linear function that will shatter many of the configuration. There are no linear functions that can shatter them. But if I go with more expressive functions, something like this, then I can do whatever I want for these 13 points, right? I can shatter them any way I want. So this intuition is the intuition I want to build here, right? So we're going to say that a set S of examples is shattered by a set of functions H if every partition of the examples in S into positive and negative examples can be expressed using some function in H. That is, there is some function in H that gives exactly these labels to the examples. So what I've showed you is I showed you the example of 2 points, and I showed linear functions are sufficient because every partition of the examples in the set S of 2 points was realizable by linear functions, right? There were only 4 options, and each one of them was realizable by some function, some linear function. But the set of 13 points, there are so many ways to partition them to pluses and minuses, and linear functions are not sufficient for it. So that's the intuition we want to pursue here. And I'm putting here the definition again so that we can play with some examples. Now, the intuition here is a rich set of functions shatters a larger set of points. So let's take a very simple set of functions. This is the set of functions that is parameterized by the number A in the set of left bounded intervals on the real axis. What do I mean by that? Positive examples are all the number between 0 and A. Negative examples are outside, to the left of 0 and to the right of A. So how many examples can I shatter with this? Anyone wants to jump up with this? Here's the set of functions, right? So positive between 0 and A, negative outside 0 and A. So I want to claim that I can shatter 1 point this way, right? So if you give me 1 point, I can put the interval around this point. Maybe the point is 5. I can put an interval around it and make it positive. I can put the interval below it, let's say between 1 and 2, and then this point 5 becomes negative. So 1 point I can shatter. What about 2 points? Can I shatter 2 points with this set of functions? Let's assume my 2 points are 5 and 10 on the real axis. So the case that both of them are positive, I can do, right? I will put an interval from 1 to 100. So the points 5 and 10 are going to be positive. The case that both of them are negative, I can shatter. If they are 5 and 10, I'm going to make the interval between 1 and 2. So both of them are going to be negative. What about the mixed case, where 1 is positive and 1 is negative? Do I have an interval that expresses both labelings? So hopefully your answer is no, because if I have 5 and 10, I can put 5 as the positive and 10 as the negative by putting an interval between 0 and 7. But I cannot make 10 positive and 5 negative. Hopefully that's clear. So let's move on to a slightly more complex examples. So I want to go to the set of, so this is the explanation of what I just said before. Set of 2 points cannot be shattered, right? And hopefully you're convinced about this. So let's move on to a more complex set of functions, set of intervals on the real axis, A to B. So again, positive examples here are between A and B, negative examples here are outside A and B. So look at this case, and I want to know how many points can be shattered by this kind of function. So this is a question that I want you to answer now. How many points can you shatter with real intervals? So again, positive examples are between A and B. Negative examples are below A or above B. So think about the case of 1 point, 2 points, 3 points, 4 points. And I want to know what is the smallest set of points that I cannot shatter. Hint, it's not 1, because 1 you can definitely shatter with this. You can put the interval around this 1 point, or you can put it completely outside this 1 point to get it as negative. Think about the case of 2 points, think about the case of 3 points, and let me know what is the smallest set of points that cannot be shattered. Okay, many of you are already answering, so let's look at it. Okay, most of you think that the answer is 3. And hopefully you all have an argument for that. And let's move on to see this argument. Okay, so here is the picture. And clearly for 2 points, everything is going to be okay, right? Because I have 4 options for 2 points. I can make both of them positive by putting the A and B around them. I can make both of them negative, but putting the A and B a lot below them or above them. And I can also make 1 positive and 1 negative. If the positive, I can put the A and B around the positive, leaving the negative outside. And it doesn't matter whether the positive is smaller than the negative or larger than the negative, because I have negative on both sides of the positive. What about 3 points? 3 points is the tricky case, because for 3 points, first of all, you have to realize that for 3 points, I have 8 configurations, right? 3 points I can label in 8 different ways, all positive, all negative, the smallest one positive, the second from the small positive, the largest positive, and so on. But there is one configuration that I cannot express, right? And the one configuration that I cannot express is that if I have 3 points on the line, I cannot make the middle one negative and the other 2 positive. I cannot do it with these kind of functions. And therefore, I cannot shatter 3 points. Questions on this? Okay, hopefully that's clear. Let's move one step more to a very interesting class of functions that you all know, half spaces in the plane, or another way of saying linear functions. So in this case, I have linear functions. That this linear function separates these pluses from minuses, and I'm going to ask the same question. So how many points can I shatter with linear functions? So it should be clear to you that sets of 1, 2, or 3 points can be shattered. But let's think about 3 points. The case of 3 points is kind of tricky, because if I take 3 points on the line, right? So they're on the same line, the 3 points. I cannot shatter them with a linear function. Think about it. Again, there is the configuration of minus in the middle and pluses on two sides. I cannot separate it with a linear function. However, 3 points in the general setting, think about the triangle, then I can shatter. Any of the 8 configuration of these 3 points, any labelings of the 3 points, I can do it. So, but that's okay, because look at the quantifiers that I have here in the definition. A set of S example is shattered by a set of functions if for every partition of the set of examples in S into positive and negative example, there is a function in H that gives exactly these labels. So some sets of 3 points can be shattered. What about set of 4 points? I claim that no set of 4 points can be shattered. And this is, we have to think a little bit about it, and I want you to think about it. I'm going to give you these hints. So think about the 4 points. And let's assume that they form a convex polygon for a second. If they do form a convex polygon, then I can label them in such a way that they cannot be shattered. How will I do it? I would just alternate the positive and negative. So in this case, there's no linear function that can agree with this labeling. Now, you have to think about the case, because I say no set of 4 points. You have to answer the question, what if they do not form a convex polygon? Right? So one case like this is that if 1 point is inside the convex polygon defined by the other 3. So think about the triangle, and the 4th point is inside it. Again, I can label it in such a way that a linear function cannot agree with it. Right? So think about this, convince yourself that we can do this, and convince yourself that because of that, some sets of 1, 2, or 3 points can be shattered, but no set of 4 points can be shattered. And this distinction, the quantifiers here are really, really important. And that leads me to the most important definition of VC dimension. Again, I'm going to repeat the motivation and then define. So the motivation comes from shattering, right? So if I have a hypothesis space that is completely unbiased, all the functions are there, then I can shatter any set of points, right? Because every labeling that you're going to give me, there is a function that expresses it. But in general, if I don't have an unbiased hypothesis space, so I have a limited set of functions, then the larger the subset of X is that can be shattered, the more expressive the hypothesis space is. So I'm going to measure the expressivity of my hypothesis space as a function of how many examples it can shatter. And this leads me to this definition. So we gave you the definition of shattering, and as a function of that, the VC dimension of the hypothesis space, H over instance space X, is the size of the largest finite subset of X, then that is shattered. Okay, so I don't care that all the subset of this size will be shattered. I want just to find the largest one that is shattered. Right? So in the case of linear functions that we looked at before, I showed you that no set of 4 points can be shattered, but some sets of 3 points can be shattered. So the largest finite subset of X that can be shattered by linear functions is going to be 3. Because some subset of size 3 can be shattered, but no subset of 4 can be shattered. So even if only one subset of this size does it. So it's important really to understand these quantifiers here. Okay, so basically that means that there are 2 steps to proving that the VC dimension is D. One is if there exists a subset of size D that can be shattered, then the VC dimension is at least D. If there is no subset of size D plus 1 that can be shattered, then the VC dimension is less than D plus 1, which means these 2 together, it's D. So next time we're going to start with these 3 examples, but I want you to think about it already. In all 3 examples that we discussed so far, we actually determine the VC dimension, half spaces in the plane, intervals, and half intervals. And I want you to make sure you understand why this is the case, that this is the VC dimension. So go back directly to the definition. In the case of half intervals and intervals, it's very simple. In the case of half spaces, it's a little bit trickier because some subsets of size 3 can be shattered, but some are not. But it's still okay from the perspective of this definition. Questions before we end? Okay, so really this is a tricky concept, and you should think a little bit and play with it a bit more to kind of digest this notion. We're going to basically start and finish with this next time. And the key thing that I want to show is that really the key learnability results that we showed, which is this Occam's razor algorithm, makes use of the VC dimension. That is, I can just take a set of examples and replace the theorem that I had before, where M is greater than 1 over epsilon, something that has to do with the size of H, and something that has to do with delta, and replace the size of H with this VC of H. The constants do not matter, but basically what we've shown is that, or what we claim, is that given a set of M examples, if I can find an H that is consistent with these M examples, where M is this, that is, scales nicely with the VC dimension, then everything is going to be okay. That is, with high confidence, the error of this H is going to be less than epsilon. So that's a key point. Oh, okay, so I want to finish with another thing that I want you to think about, which is I showed you something for finite H's, and now we gave a theory for infinite H's, which we're going to go back very, very quickly at the beginning of next Wednesday. But are these 2 distinct theories? What if H is finite? And it turns out that they are not distinct. I can actually compute the VC dimension also for finite hypothesis spaces. And here is the way I want to think about it, and I want you to think about it. So let's assume that H is actually finite, and it can shatter K examples. I'm claiming that because it shatters K examples, the size of H must be at least 2 to the K. Why? So that's your homework. Once you understand the last few slides of shattering and VC dimension, you'll be able to answer this why, and we're going to start with this next time. So try to come up with a good answer, a concise answer for why is it true that for a finite h that shatters k examples, we know that its size is 2 to the k. Because if you understand this, you will understand that the log of h, which is used to be our complexity parameter for finite h's, is at least as large as the VC of h. So we connected these two notions of size of h and VC of h for the case of finite hypothesis. Questions? Okay, so let's end here. I realized that these last few minutes were, I think, hopefully interesting, but also challenging. So please go over the slides. They are all on the website. And be ready to answer these questions and a few others on Wednesday. Thanks. See you Wednesday.
Thanks, Professor.
Thank you.